Chen-Ning Yang, the physicist who revolutionized our understanding of the universe. Chen-Ning Yang. The physicist who revolutionized our understanding of the universe. Chen-Ning Yang, a pioneering Chinese-American theoretical physicist, has died at the remarkable age of 103. Renowned for his groundbreaking work that overturned long-held assumptions about the fundamental forces of nature, Yang's legacy includes a Nobel Prize and a profound impact on modern physics. His contributions laid the groundwork for the standard model of particles and forces that shapes our understanding of the universe. Overthrowing mirror symmetry and a Nobel Prize. Yang's ascent to global recognition began in 1957 when he was awarded the Nobel Prize in Physics. This prize was shared with his close friend and fellow immigrant, Tsundao Li, for their work challenging the widely accepted parity laws. These laws proposed a fundamental symmetry in the forces acting on subatomic particles, suggesting that a mirror image of any experiment should yield the same results. Yang and Li demonstrated, through rigorous theoretical work, that this mirror symmetry was not universally true. The birth of Yang-Mills theories, while the Nobel Prize recognized the parity violation work, perhaps Yang's most enduring contribution came earlier, in 1953. Working with a doctoral student, Robert Mills, Yang conceived of a revolutionary theoretical framework that would become known as Yang-Mills theories. This brief collaboration, originating from a visit to Brookhaven National Laboratory, unexpectedly led to a monumental breakthrough. These theories now form the bedrock of modern particle physics, successfully describing the weak and strong nuclear forces of the four fundamental forces governing the universe. Initially, however, the theory faced harsh criticism, notably from the influential and notoriously exacting physicist Wolfgang Pauli, who nearly derailed Yang's burgeoning career. Understanding gauge invariance and the challenges of mass. The core of Yang-Mills theories lies in the concept of gauge invariance, a profound property of quantum field theory that severely restricts what is physically possible. This concept, demonstrated in the successful theory of quantum electrodynamics, QED, mandates that physical laws remain consistent regardless of location or measurement system. A key consequence of gauge invariance is that fundamental particles like electrons must possess the same charge, a seemingly obvious fact that emerges from a deep mathematical principle. To build a similar theory for the nuclear force, Yang and Mills's equations accounted for the flow of electric charge between protons and neutrons. The resulting theory predicted the existence of three distinct varieties of massless vector particles, one electrically neutral, like light, photons, and the others electrically charged. However, when Yang presented this theory at Princeton's Institute for Advanced Study in 1954, Wolfgang Pauli's pointed questioning nearly silenced him. Pauli famously inquired about the mass of these predicted particles, instinctively realizing they would have to be massless, a notion he found challenging. It wasn't until 1964, with the groundbreaking work of Peter Higgs and others, that the puzzle of mass was solved. They posited the existence of the Higgs field, which explains why these vector particles, now known as W and Z bosons, can acquire mass. The 2012 discovery of the Higgs boson provided definitive empirical confirmation of this mechanism. From quantum chromodynamics to the standard model, Yang-Mills theory also forms the basis for quantum chromodynamics, QCD, which describes the strong nuclear force binding quarks within protons and neutrons. These quarks carry a property known as color charge, and the force between them is mediated by massless vector particles called gluons. The existence of quarks and gluons and the validity of QCD were confirmed in the 1970s. Combining Yang's insights on gauge invariance, the violation of mirror symmetry, and the Higgs mechanism, we now possess the standard model of particles and forces, a triumph of 20th century physics. A life in physics and academia. Born in Hefei, China, in 1922, Yang's journey to becoming a leading physicist was marked by intellectual brilliance and perseverance. He excelled in mathematics and physics, earning his Ph.D. from the University of Chicago in 1948 under the guidance of Edward Teller. After a distinguished career at the Institute for Advanced Study, Yang joined Stony Brook University in 1965. In his later years, he played a pivotal role in establishing large-scale research centers in China. eventually renouncing his U.S. citizenship in 2015. Beyond his monumental work in particle physics, Yang made significant contributions to statistical mechanics and condensed matter physics, and received numerous awards, including the National Medal of Science. He was married twice, first to Chilai Tu, who passed away in 2003, and then to Wang Fan, who survives him, along with his children. Chen-Ning Yang's legacy extends far beyond his Nobel Prize. He fundamentally reshaped our understanding of the universe, leaving an indelible mark on modern physics and inspiring generations of scientists. The death of Chen-Ning Yang marks the end of an era and leaves a world profoundly grateful for his genius and enduring contributions to science. His work represents a cornerstone of our knowledge of the fundamental forces that shape our reality.